What's up, Sigma fam? It's your boy Chris from Sigma Science Education. We are here to try and get through some of these misunderstandings that often arise because of parallel circuits. Odds are you've looked at series circuits, year 9 or year 10, and everything kind of makes a bit of sense. You chuck in more resistors, you get more resistance, you get less current, and everything is kind of happy. You might have been introduced to parallel circuits in year 9 or year 10. You wouldn't have done, well, most likely you wouldn't have done any kind of quantitative stuff when it comes to the parallel circuits. The quantitative stuff of parallel circuits is kind of really reserved for year 11. And when we start to get into the quantitative analysis of these parallel circuits, often students are basically like this. Like, what's going on with these parallel circuit thingies, Series circuits make perfect sense. Add more stuff, get more resistance, get less current. Parallel circuits, add more stuff, get less resistance, get more current. Usually teachers will say, especially if they're a biology teacher, usually teachers will say something like, oh yeah, it's because the current has more choices, it has more freedom, and more freedom gives more current, and all this sort of fang-dangly stuff. I actually want to explain to you why it is the case. Why does resistance in a parallel circuit actually go down as you add more stuff, or what we're going to end up calling more branches? So hopefully we'll dispel this WTF, okay? And we'll just replace that WTF with a 3, and then everything is going to make sense. So this is all going to be one take, no editing. I will make mistakes, I guarantee you, but it doesn't really matter because we're all gonna learn together. All right, so what do you need to know? Couple of things, and hopefully you're familiar with both of these things before you listen to this video, before you watch this video. Ohm's law and Kirchhoff's laws. Most important thing in year 11 physics is this guy down here. You do not pronounce it as Kirchhoff. If you pronounce it as Kirchhoff, all I'm going to say is bless you. Okay, it is Kirchhoff. Okay, if your teacher says Kirchhoff, slap to the face. All right, so anyway, Ohm's law. Ohm's law you guys are all familiar with. Okay, so V is equal to IR, or I is equal to V on R, or R is equal to V on I, whatever. Okay, we're going to use 1 or 2 or 3 of those particular arrangements. Kirchhoff's laws, again, you should be familiar with. Sum of all voltages in a closed loop is equal to 0. Okay, we're not taking into account any other kind of induced EMFs along the way. So sum of all voltages in a closed loop is equal to 0. But the most important one for the parallel circuits, which we're going to be looking at, is the fact that the total current is just going to be the sum of all currents, kind of, let's say here's a junction, and you got these kind of things going in here or whatever. Okay, and there is like the total current coming out. The total current coming out is the sum of the currents going in, or kind of vice versa. In general, just all the currents coming out of a junction or a node or whatever you want to call it, is equal to the sum of all the currents going into the junction, okay, or into the node. If you remember those two things, parallel circuits, chef's kiss, going to make perfect sense. All right, so let's go through it. I don't want to go backwards, I want to go forwards. Here we go. How to derive the formula. Most importantly, you've got to get out of the mindset of thinking about, hey, I'm adding resistors in a parallel circuit. Okay, I don't want you to think about the resistance in terms of resistance. I want you to think about what happens to current, and then we're going to translate that to resistance. Again, you'll see what I mean as we kind of go through the next few slides. But essentially, consider here, we've just got a closed loop. Now, there's some sort of voltage source here, whatever it is, it's a battery or whatever. Okay, now, side note, different teachers will want batteries drawn differently, okay? Some will just find you doing kind of like a single, small line, big line. Some want multiple small line, big lines. Some will want little dots in there. Whatever your teacher wants, you just draw whatever your teacher wants. Some teachers will want this little diagonal line through there because you're using a variable power supply in class, whatever. Okay, whatever your teacher wants, just make them happy. Okay, don't worry too much about it because circuits do not come up in year 12. Okay, so it's something you either love or hate. If you love circuits, you're going to not like year 12 in terms of there being no circuits in there. But a lot of students do find it confusing, and they're pretty happy when we don't go through any circuit stuff in year 12. Okay, so what I want us to consider, right? So firstly, it's just, this is my total current through the circuit. Okay, so it's the current coming out of the power supply. Now there's really only one pathway for that current to flow, and that's through R1. So we'll just call the current I1, okay, just denoting that it's going through resistor R1. It would be fair to say, if I take a little junction here, just call it label A. Just call it label A. Nice, there we go, first mistake. Label it as point A. We'll say currents in is equal to current out. Makes sense, right? All the currents flowing into junction or node A is equal to all the currents flowing out of junction or node A. All right, cool. Second mistake there. I forgot to put that little thing there on. It's on now. Nice. All right, so the total current through the circuit is just going to be the current through resistor 1. You with me so far? Let's move on and introduce a second branch. All right, so with the second branch, still the same voltage and everything. Again, I'll just put a V here. So it's just our voltage, douche, douche, douche. And we've already said this is the total current. And we've labeled this current through resistor 1. All right. What we need to see now is there's also going to be current that goes through resistor 2. And the current that goes through resistor 2, we are just going to call I2. So now the total current through the circuit is I1 plus I2. Really important to note that this value of I1, it's exactly the same value as I1 from the previous page, okay, when there was only one loop. And the reason behind why it is still the same value is if I get rid of this dodgy V and I put in my little power supply again, douche, and let's say that has a voltage of V. Generally, what that means is the positive terminal is at a potential of plus V and the negative terminal is at 0. Okay, now we make an assumption in year 11 and year 12 if needed, and that is that all the wires in a circuit have exactly 0 resistance. So if it has 0 resistance, according to Ohm's law, it doesn't matter how big the current through the wire is, there'll never be a voltage across it. So there's no potential difference in the wires, which means down here where we have the 0 volt terminal, everything connected directly to that 0 volt terminal is also going to be at 0 volts. So both are kind of like the bottom sides, let's call them. So both these bottom sides are at 0 volts. And when you consider that the positive terminal is at plus V, both of the top parts here and here, they're both going to be at plus V as well. So the previous page where it was just one loop, we had a potential difference of V across the resistor R1. Now we've still got a potential difference of V across resistor R1, which means the current is just voltage divided by resistance. So if the voltage value hasn't changed and the resistance value hasn't changed, the current value has not changed. Okay, so that's an important thing to remember. By introducing more of these branches, we actually do not affect the current in any other branch. Okay, all that happens is we just get more current, and this is where this whole parallel thing is going to start to make sense. Every single branch we introduce gives rise to more current, okay, and that current flows through that branch. That current will also make up our total current. Okay, so we'll see again, as we add more branches, we just get more current. All right, with me so far? So all we're going to do now is we're going to add a third branch, and it's legit exactly the same stuff. Here is our third branch. Okay, I'm going to chuck in my power supply again. So my power supply with a voltage of V. Everything at the top is at a potential difference of plus V. Everything down the bottom is at a potential difference of 0. So the voltage across each resistor is V. And yeah, it kind of seems like you're cheating a little bit, I suppose, is you're like, oh, there's a voltage of V here. How can I have V across this and V across this and V across this? It's like I'm getting 3V. I'm violating conservation of energy, or something like that. We'll see, we're not. Okay, we're not doing kind of any extra work, let's say. What's actually going to happen is we're going to get more current out of the battery, which I suppose you could kind of treat it as like the battery will, discharge more quickly, let's say. All right, so we've got, let's chuck in our little currents, I1, I2, I3. So once again, it would be fair to say in terms of Kirchhoff's current law, the total current is just I1 plus I2 plus I3. And if we introduced a fourth and a fifth and a 763rd branch, it will just be plus I4 plus I5 plus I763 or whatever the hell I said. I completely forgot already because I'm 40 years old and I forget everything. All right, so there we go. That's what I want us to think. More branches, more current. Now let's actually go through and derive the equation. All right, so once again, plus V, plus V, plus V. 0, 0, 0. Okay, chucking our power supply again. V. Now we also say this is our current IT. This is our current I1. This is current I2. This is current I3. Okay, and you've agreed with me. Shut up, dog. You've agreed with me that the total current is I1 plus I2 plus I3. If that makes sense to you, the derivation is going to make sense to you. Okay, because very commonly students say, why in series, why is the resistor in the numerator, and why in parallel is it in the denominator? Well, I'm going to show you exactly why that is the case. So firstly, total current. Okay, so this is just Kirchhoff's current law, pretty much. And then we have our Ohm's law. Dush. All the parallel resistance formula is a happy little marriage between these two things. The total current through the circuit. So I'm just going to redefine the currents here in terms of voltage on resistance. The total current is really simply just the total voltage over the total resistance. Current through resistor 1 is just going to be the voltage across resistor 1 divided by the resistance of resistor 1. And then we'll do the same thing for all the others. Okay, so we're just rewriting, we're just rewriting the expressions for the current through the different branches. Okay, now, oh, my big head's in the way. Let me just shrink my head for a second. Awesome. So here we go. So we've got our voltages, we've got our currents, we've got our voltages and our resistances. One thing that we need to keep in mind is this is a purely parallel circuit. In a purely parallel circuit, the voltages across the resistors are the same. And they're all equal to the supply voltage. So at the top here, VT is equal to V1, which is equal to V2, which is equal to V3. So what might we do here? What we might do is I might get rid of all this and just call everything VT. Can you see where I'm going with this? I hope you can see where I'm going with this. You notice that VT is common to both sides. Oh my God. So what if we divide both sides by VT? Well, if we divide both sides by VT, we end up with this. My big head's going to be in the way again. Oh, there we go. Oh yeah, I'll talk like this. There you go. We have now derived, I don't know, whatever. I did standard English. We have now come up with, there we go. We have now come up with the parallel resistance formula simply by remembering two things: Kirchhoff's current law and Ohm's law. Putting them together, now hopefully it makes perfect sense. So again, I would encourage you not to think about parallel circuits as resistance goes down. I would want you to think about parallel circuits as current goes up, therefore resistance goes down. Because, I mean, what is resistance? Resistance is a ratio of voltage on current. The voltage doesn't change. Okay, the voltage is this guy here. If I add in more resistors, I get more currents. And if I get more current, then I have a lower resistance. That's how you need to think about parallel circuits to try and start making this stuff make sense. All right, so let's then, I suppose another good thing about this is like you actually don't need to remember how to derive this equation because it's in your formula sheet. Okay, it's not beyond the realms of possibility that perhaps, in a school exam, they may ask you to prove it. Like prove the parallel current carrying conductor formula, or some parallel current, I better not say parallel current carrying conductor. That is something in year 12. Prove the parallel resistance formula, okay, or something like that. Not beyond the realms of possibility. Oh, back to the big head. All right, So let's have a look at how to solve problems. So how to solve problems in parallel circuits, it's really just like 3 steps. Find the equivalent resistance. Okay, you may not need to do that. These are like 3 things that you need to do. You may not need to do all of them. Find the equivalent resistance. Use voltage to find current, or use current to find voltage. Now you'll see this guy here. This is what you can use to solve, basically the hardest circuits you can get in year 11 and year 12. All right, so those 2 things, you just flip back and forth between them. You'll see when we do some combination circuits in another video. Okay, and then step 3, if you want to be, nice and thorough, ensure that Kirchhoff's voltage and current law are always upheld. Okay, every circuit you do in year 11, that will be upheld. So here's one that I found, which I haven't actually gone through how to do it yet. So I'm going to be working it out with you as for the next one, because I kind of wanted to grab a couple of examples and I wanted to show you my brain thought. Well, that's not right. My train of thought, my brain of train. I'm legit lost. My train of, I don't know, my train of thought, right? I want to show you how I think about solving problems. So example 1, we've got parallel circuits, and it says, like, these are just 3 things that you might have to do. You may not have to do all of them again, but we'll go through how to do each one to try and make you happy. All right, so example 1, parallel circuit. First thing, find total resistance. Now they did have killer ohms on this. I just got rid of the killer, okay, because I was like kind of Siebes timesing everything by 1,000. So find total resistance. Let's go. Find total resistance. I'm going to bring up my calculator. Doosh. Find the total resistance for this. Okay, you can see my little cursor, hopefully. So total resistance, so we're just going to do our little formula. So 1 on RT is equal to 1 on R1 plus 1 on R2 plus 1 on R3. Okay, do keep in mind, like, probably the most common thing that students forget to do when using this parallel resistance formula is at the end when they get their solution, they forget to flip it, okay? Forget to do the 1 over. Okay, so we solve for 1 over RT. So 1 over RT is going to be 1 over 10 plus 1 over 2 plus 1 over 1. Okay, some people like doing things in their head. I'm more than happy for you to do things in the head. So let's go, find everything, the common factor or whatever it's called. So we go 1 on 10 plus 5 on 10 plus 10 on 10, okay, which is going to give us 16 on 10. Therefore, RT is going to be 10 on 16. All right, so first thing to see is I'm happy with this. I can't even talk. I'm happy with this value. Okay, and there's the reason why I'm happy with this value. The reason why I'm happy with this value is in parallel circuits. So in parallel circuits, here we've got a 10, a 2, and a 1. The equivalent resistance is always less than the lowest value resistor. Okay, it's always less. My lowest value resistor is 1. Therefore, my total resistance should be less than 1. Okay, so if I, forgot to flip it, I say, oh, I get 16 on 10. I'm like, well, shit, that's 1.6, which is obviously greater than 1. What have I done wrong? Oh, I forgot to flip it. Oh, awesome. Okay, now 10 over 16, I can't do that in my head, but I'm totally going to have a go. I would say, why am I multiplying everything by 6? Okay, so that's going to be about 0.62. 0.62. Let's go. 10 divided by 16. Bro, dude. I'm off. All right, I'm going to keep this in 3 sig fig just so I get the first 2 digits right. So RT is 0.625 ohms. There we go. Again, less than 1. Makes me happy. So second part of the question is to find the total current. So total current. There's a couple of different ways you can do this, and I want to show you both. So the first thing is to use that value from the previous question. So 0.625. We can just straight up do that. So I know that total current, according to Ohm's law, is total voltage divided by total resistance. Total voltage is 9 divided by 0.625. So that'll be 9 times 16 over 10, which is 15.4. I can't do that in my head. Oh, maybe 15.4. Let's try it. 9 divided by 0.625. 14.4. Boo. 14.4 amps. Okay, 9 plus 5.4 is not 15.4, Chris, just to let you know. There we go. Okay, so 14.4 amps. Alternatively, Okay, there is another way. If you have not found out the equivalent resistance, there is another way for you to do it. Okay, so I'll just get rid of this way. So that's kind of method one. Find the total current using total voltage and total resistance. Second method is if you think about Kirchhoff's law, right? Kirchhoff's current law, it would be fair to say that IT is equal to I1 plus I2 plus I3. Is that not fair? I believe that is fair. So what if we just find I1, I2, and I3, which we can because we have the voltage across each resistor and we have the resistance of each resistor. So that's just going to be 9 on 10 plus 9 on 2 plus 9 on 1, which again is going to be our 14.4 amps. Doosh. Okay, so 0.9 plus 4.5 plus 9 is going to give us 14.4. So there we go. Okay, just make sure at the end of that, like if you just did I1 plus I2 plus I3, I probably wouldn't give you full marks because you've not told me that this is equal to IT. So sketch, label, whatever, annotate the diagram, show me IT going in, I1, I2, I3, IT is equal to I1 plus I2 plus I3, solve for I1 plus I2 plus I3, and you've told me that's equal to IT. Makes me happy. Makes me happy. You got to do everything perfect. It's not hard. Okay, physics is not hard. You just got to do everything perfect all the time. Sounds harder than it is. Actually, that's pretty hard. All right, so let's find the current through each resistor. Well, guess what? We've actually already done that. Boom. I got ahead of myself there. Okay, so you can just, oh, you know what? I'm going to cheat a little bit. So I'm going to go and I'm going to, so here's what happens when you just do everything in one take. You forget what the next question is. Here's one I prepared earlier. Doosh. Ha, ha, ha. All right, so yeah, same deal. Okay, exactly the same deal. So you can find the current through each one. Say it's equal to the total. They may specifically ask you to find me the current through resistor 2. Or whatever. Okay, but that's what we've done here is we've used voltage to find current. Okay, so we've used this value of voltage here, the 9 volts, to find the current through the resistors. The other scenario is you use current to find voltage. Okay, and again, haven't done this question yet. Oh, not even up to it yet, but here we go. I think, what? Yeah, sorry. Here we go. This is the example that I was talking about. So I haven't done this yet. Okay, so this is all going to be from my noggin. So let's just hope I get it right. So once again, there are a couple of different ways of doing this type of question. So you notice you've got current going in. You've got the resistances here. And remember what we know about parallel resistors. They all have the same voltage. Okay, so here is the voltage. Like say there's a voltmeter or whatever wired across here. It's the same voltage across resistor 1, 2, and 3. So let's go I2 and I3, right? So let's firstly say, well, let's call this, I like labeling things as IT. Okay, so IT is I1 plus I2 plus I3. Okay, another thing you'll notice about my writing, I never got my pen license in primary school. Okay, never, ever, ever. But for some reason, I didn't end up being a doctor. Don't know. All right, so let's have a look. 42 is going in. Now we've got these individual resistors, and we know the voltage across each one is constant. Whatever shall we do? Okay, the first way of doing it is to find the equivalent resistance. So do the parallel resistance formula, resolve it into one resistor, and then we can use voltage is equal to current times resistance to find the voltage across the parallel resistors, and then do Ohm's law 3 times to find the current through each one. That's the long way, which I'll go through first, okay? Because I find it's the way that students tend to make less mistakes. So let's go through. All right, so firstly we'll say our total resistance, parallel resistance formula, 1 on RT, is 1 on R1 plus 1 on R2 plus 1 on R3. Okay, now again, I'd encourage you not to do stuff in your head, even if you're really good at math. Sometimes under exam situations, you have brain farts. Everyone has brain farts. Part of my job is to minimize these brain farts that you have. So 1 on RT. So I'm going to use a calculator. which I probably need anyway, to be honest. Plus 1 on 24, plus 1 on 48. Okay, now keep in mind what we said about parallel resistors. The combined resistance is always less than the lowest value resistor. So I'm expecting my RT to be less than 6. So let's do this in our little calculator. So I'm going to do this. So it's 1, how do I go down? Is that, yeah, cool. 1 on 6. And then I'll go plus. So we got 1 on 24, 1 on 24, plus 1 on 48. Okay, is 11 on 48. So 1 on RT is 11 on 48. And don't forget to flip. We therefore got to say therefore RT is 48 on 11. Okay, some teachers want you to round off for sig figs here. Whatever, I don't really care about sig figs. Okay, so 48 on 11 ohms. All right, and then we're going to find the voltage across the combined parallel resistance. So what we've done here is we've reduced these 3 resistors to one effective resistor, and therefore to find the voltage across, we're just going to do our regular Ohm's law. We're going to say V is IR, which is 42 times 10 to the minus 3. So don't forget any prefixes, right? Milli, micro, nano, you got to know all those guys. Okay, multiplied by 48 on 11. Okay, so I'll just chuck in, oh sorry, I'll do a 1 over here. Where's my 1 over, oh, here we go, douche. Answer minus 1, douche, 48 on 11, times 42 times 10 to the 3, where's the minus? Oh, don't tell me I have to do the minus first. Oh, you suck. Minus 3. Douche. All right, so we get a voltage of 0.183 volts. So that's the voltage, let's just assume down here is 0. So that's the voltage up here, 0.183. So therefore, across each branch, we have 0.183 volts across each branch, so we can find the current through each one. Okay, I might just get rid of this stuff down here now. We've done that. Douche. So we'd say current through resistor 1 is just going to be the voltage across resistor 1, which is my 0.183, divided by 6. Current through resistor 2, same deal, right? 0.183 divided by 24. Current through 3 is going to be 0.183 divided by 48. Douche. Okay, you notice these are all in nice ratios. Okay, so let's go divided by 6, and that's going to give me 0.03, 05 amps. And I'm going to divide that by 4, which will be in total divided by 24, 0.007636. And then I'll divide that by 2, which will be in total divided by 48. 0.003818. Now, if I add them together, they should all equal 42 milliamps. So 0.042. Let's have a look. Plus 0.007636 plus 0.0305. All right, sweet, cool. Okay, except for, rounding errors, to 2 sig fig, this is 42. Okay, and to 3 sig fig is 42.0, so that makes me happy. All right, cool. Don't forget units. Always penalize all my students. Okay, so here's our final answers for the current through each one. All right, so that's the first way, which is the long way. So it's essentially you finding the effective resistance of the entire the entire setup, all the branches combined, using that resistance multiplying by the current to find the voltage across the combination, and then using I is equal to V on R across each individual branch. You notice that it takes quite some time to do. That's the approach that I would recommend basically everyone to do. If you like ratios, there is a faster way. I'll show you how to do it, but again, I would encourage you still to do it this first way, okay, rather than doing the ratio way, because I tend to find even with the really good mathematics students, you make silly mistakes. Now, watch me make a silly mistake during this. Again, I haven't done it yet, so I'm hoping that I don't make a silly mistake, but odds are, it's me, odds are I'm going to. Okay. So firstly, you got to keep in mind again, the voltage across each one is constant. Okay, the voltage across each one is constant. Now we know V is equal to I times R. We know this, right? So that means I times R is also constant, which means I is inversely proportional to R. So there is the most current going through the lowest value resistor, and the least current going through the highest value resistor. So what I would generally do is I would look for the highest value resistor, and I'll just call that current, this is the third resistor, so I'll call that I3. Now, if I look at, like, everything's kind of nice in this question because everything's in ratios. Okay, nice full integer ratios. Here, it's half the resistance of that. Therefore, there should be twice the current. So this is going to be 2I3. Okay, and then likewise, going from I3 to I1, we notice this is 1/8 of the resistance of that. Therefore, there should be 8 times the current. So we have 8I3. What do we do next? We do Kirchhoff's current law. And we say that the total current here, which we know is 42, is just the sums of these currents. Now, because it's not, I1 plus I2 plus I3, there's just the one little variable in here. It's I3 plus 2I3 plus 8I3. So we'll just say, well, 42 times 10 to the minus 3 is 11I3. Therefore, I3 is 42 times 10 to the minus 3 over 11. Now, hopefully that kind of marries up with the value. What do we get? 0.003818. Yeah, it is. It is going to be correct. 0.042, that's my 42 milliamps divided by 11. Lo and behold. Now, that is way quicker, right? Way quicker. And then we just, what am I doing? Oh my gosh. That's annoying. There we go. Ah, man. Look at that mistake. Now, I'm not going to edit that out because I said I'm not going to edit anything. All right, so yeah, we've got the current through my resistor 3. Doosh. And then we'll just go back to these. So this is going to be twice times that. So I'll just multiply this value by 2 to find the current through that. And I'd multiply this value by 8 to find the current through that. And then I'd have the current through each individual branch. So yeah, I'll say to you kind of like, use that sparingly. Like in terms of, I just tend to find when students use ratios in parallel circuits, ratios, mostly everywhere else, ratios are fine. But in parallel circuits, for some reason, students like to stuff it up. Okay, so do it the long way, unless you're 127%, at least 127% confident in your mathematical ability. So there we go, Sigma fam. Again, my name's Chris. Hopefully that helped you with your understanding of parallel circuits. Watch out for more videos where we're going to tackle some harder combination circuits. Ciao, peeps.